Hey, hello. Okay, good morning, all of you. Today, we are going to start our new machining process. Okay, under mechanically energy based non-conventional machining process, and the process name is called ultrasonic machining. Okay, so in this lecture, in part one, we are going to cover the with a basic question, that is what is meant by ultrasonic. Okay, then we are going to going for the block diagram of working of ultrasonic machining system. Okay, and then we'll see the working principle of ultrasonic machining. In short, it is called USM. Okay, so this is just a points to be covered. Okay, so that I have mentioned here, and after that in the part 2 we are going to see the another points. Okay, so let us start with the introduction, and in the introduction we'll cover the first question, that is what is ultrasonic. Okay, so as we know that ultrasonic means what? Ultrasonic is a vibratory waves having frequency greater than the upper frequency limit of the human ear. Okay, once again repeat. Ultrasonic is vibratory waves having frequency greater than the upper frequency limit of the human ear. Now, what is that upper frequency limit? Okay, that means it is greater than or equal to 16 kilohertz. Okay, that much frequency, more than that much frequency, if vibratory waves will be there or no, so that time we can call it is a ultrasonic. Okay, now again that 16 kilohertz means what? 16,000 cycles per second. Okay, simply we know that. Now this is a ultrasonic. Now in that again, we'll have the different types of waves. Okay, so there are basically two types of waves. Okay, you can see here also there are two types of waves. One of them is known as longitudinal waves. Okay, here I have written in the red color. Okay, and another it is known as shear waves. Okay, so these are the two types of the waves. Now in that again, in case of our ultrasonic machining USM, okay, we normally use longitudinal waves. Okay, in case of our ultrasonic machining, we normally use longitudinal waves. Okay, so they easily propagate in the solid as well as liquid and as well as in the gas. Okay, so this is a plus point about the longitudinal waves. Okay, because these are easily propagate in solid medium, then liquid as well as the gases. Okay, and in our ultrasonic machining process normally we use the this type of waves, longitudinal wave. Okay, now in that again, uh, uh, to generate the that waves we require some the transducer. Okay, so in that again we have the longitudinal magnetostriction. Okay, now the question arises, what does mean by this longitudinal magnetostriction? Okay, so what happen if a ferromagnetic material is placed in continuous changing magnetic field? Okay, then what will happen? So it results in a changing in the length of your transducer. Okay, now transducer means what? It convert the your electric energy to the vibratory energy. Okay, that means the vibrations. So again in that, what happen, if a ferromagnetic material is placed in continuous changing a magnetic field, that time it results in a change in length of your transducer, and that is placed in a continuously changing magnetic field. So this magnetostrictive type transducer is used for your ultrasonic machining process. Okay, magnetostrictive transducer, it is used for your ultrasonic machining. Okay, and they are normally made of the nickel permalloys. Okay, the material. Okay, in that again 45% is the nickel will be there and 55% will be iron. Okay, so this is composition, and there is another material you can use, that is called permeador. Okay, So in that again 49% cobalt will be there, 49% iron, and 2% vanadium. So this is again the composition of the permedia. Okay, so the material which is used for the magnetostriction type transducer, so that material are two materials. In that, one nickel permalloy, and second is the permandium. Okay, this is just for your information I am giving this. Okay, actually this in detail we should not go, but as a knowledge we should know. Okay, again these transducers are made up of the laminated sheets. Okay, because there are certain reasons for it also, okay, to made with the laminated sheet. Okay, and this laminated sheets reduce the ED current losses. Okay, that is why transducer are made up of the laminated sheets. Okay, so if in MCQ or if in exam the question will arise, ask which type of transducers is used in ultrasonic machining, then your answer should be this magnetostrictive type transducer. Okay, what is the function of transducer? Okay, what is the function of transducer? Transducer means what? Please tell me. Okay. Many times in physics, you might be heard about this. Okay. So once again, I will repeat: transducer is a electrical device, okay, which convert energy from one form to another form. Okay, in some cases, you can uh, take example like uh, your microphones and loudspeaker. Okay, again in the transducer, will have the some sensors. Okay, and actuators also, that we are going to see how the uh, your electric energy is going to convert into the vibratory energy. Okay, because vibrations are that are ultra sonic frequency vibrations will be there in this ultrasonic machining. Again, I will give one another example of transducer. That means to convert the some energy, sort of energy to sound. Okay, or to convert sound energy to the electrical signal also. Okay, so that is a transducer. Now come to the our main point, that is block diagram of this ultrasonic system. Here I have shown the block diagram, you can see. Now here, what are the ultrasound transducers are there now, so that converts your appropriate form of energy, okay, into your ultrasonic waves. Okay, why I'm taking name ultrasonic? Because we want frequency more than 16 kilohertz. Okay, to remove the metal from your workpiece, so that frequency we have to attain. Okay, and for that purpose we require the this transducer. And normally in the ultrasonic machining, electrical energy is converted into the mechanical energy. Okay, with high frequency of vibration. Electrical energy is converted into the your mechanical energy with high frequency of vibration. Okay, now let us see the what is the uh, component which is required in this conversion. So you can see, first we have to take the electrical energy. That means we need AC power supply. Then to generate that ultrasonic waves, we require generator. Okay, again we have to convert that waves, okay, to a high frequency. So ultrasonic transducer is there. Okay, then to transfer the vibrations to your workpiece, we need some tool. Okay, so tool connector will be there, and then that tool will vibrate with a high frequency. And after that tool we need some medium, okay, in between your workpiece and your tool. So that medium means the in between that your stand of distance or the nozzle tip distance we can call in terms of abrasive or water jet machining. So that gap you have to fill with the some liquid, and that's liquid normally here we are using abrasive slurry. Okay, so vibrations which are coming from the tool that will transport to your that slurry, abrasive slurry, and through that abrasive slurry, okay, it will transfer to your top surface of workpiece. Okay, and due to the impact of the that abrasive particles, okay, having again the high vibrations, so due to that impact the metal will be removed from your workpiece. Okay, so that impact you will get from the kinetic energy and the hampering action. Okay, so due to that erosion action, or erosion of the your workpiece metal will be there. Okay, and due to that continuous impact of the abrasive particle, due to the vibrations, there thousands of craters will be formed on your workpiece. Now craters means what? The small particles which are removed from your workpiece. Okay, the material which is removed from your workpiece, it is called small craters. Okay, so that craters will be the in thousands in number. Okay, and then you will get the what are the required or desired cavities. That means that you are finished component. So this much or this much we need elements. Okay, so here I have shown the block diagram. Now in continuation of this, I will explain the with this diagram. Okay, your working principle. Okay, so let us see the what is the working principle of this ultrasonic machining process. Okay, and the block diagram of ultrasonic machining system I have shown here. Okay, once again I will tell that we have the, you can see here we have AC power supply. Okay, which is connected to your this ultrasonic wave generator. Okay, and this ultrasonic wave generator, it is connected to your this ultrasonic transducer. Okay, then whatever your ultrasonic transducer is there, no, so that is connected to your tool connector. Okay, which will hold the your tool. Okay, so the you can call it as tool holder or tool connector. Okay, then ultrasonic transducer will produces the ultrasonic vibrations. Okay, and which are transferred to your tool. Okay, through this tool holder or tool connector. Okay, then tool will vibrate. Okay, at ultrasonic frequency, that means with high frequency, and between your tool, that is vibrating tool, and your workpiece, there is a slurry. Okay, there is a slurry which is consist of your liquid as well as the your abrasive particles. Okay, now that liquid may be your water, and when this tool is vibrating at an ultrasonic frequency, that time it is hitting thousands of your abrasive particle. Okay, which are present in the your abrasive slurry. Okay, and due to that hitting, thousands time hitting, okay, these abrasive particles, when they hit the your tool, no, that time they move towards your workpiece. Okay, and that time large number of abrasive particle with their high kinetic energy or high velocity, they will collide with your workpiece surface, that top surface, and as a result of that, hammering action will take place, and they erode the material from your workpiece. Okay, by creating thousands of very fine craters, okay, on your workpiece. Okay, and after that removal of the craters, you will get the your finished product or finished component. That means you will get the cavity on your workpiece. Okay, so these are the components. Okay, now in that again, what happened in the workpiece due to that hammering or that hitting of the abrasive particle. So there is a tool. Okay, normally, uh, and thousands of the abrasive particles will be there under the your tool. Okay, you can see here also. This is a your transducer. Okay, you can see the winding is there, and this is a concentrator where you can attach your tool. Okay, so this is a tool we can call our tool holder, and what a tool is there, it is also called horn. Okay, and there should be some small gap, it is called that that stand of distance. Okay, and in between that small gap we have to give a abrasive slurry. You can see here also, and then workpiece is there. So there is a tool, and thousands of abrasive particles are there under this tool. Okay, here now when this tool is vibrating, no, let us assume that it hits the due to the vibration of tool, it will hit the your abrasive particle, correct, and this abrasive particle goes and hit the your workpiece, okay, with a high kinetic energy. And due to this, or this kinetic energy is nothing but we know one of mu square, okay, that is formula. So here the m will be the your mass of abrasive particle, and v will be the velocity of with which it is hitting to this workpiece. Okay, okay, so due to that hitting, or we can call due to the hammering action, it will erode the metal from your top surface of your workpiece. Okay, now you can see here we have the transducer winding, okay, and this is a concentrator, okay, which move up and down at a high frequency. Okay, so and there is a nozzle, okay, which is supplying this is called nozzle, and this is supplying the abrasive slurry between this tool and your workpiece. Here please note down, your tool is not in physical contact with your workpiece. There is always small gap. Okay, again you can see here in large view of this particular portion, okay, whatever I have shown the red, no, so this portion you can see here. Okay, here a tool is there, then slurry, and then you have the workpiece. Okay, and during this process overcut is created through which the slurry has to go out. Okay, this is called overcut, okay, through which slurry will go, hence the additional material is removed during this process. Okay, and overcut means what? It is gap between your tool surface and the side surface of your workpiece. Okay, and some material is removed from the top that tool also. Okay, during this process, so thus you will find the material is um, continuously removed, okay, from your tool. Yeah. So here whatever the shape you want on your workpiece, no, so same shape or inverse replica we can call of your cavity to be on your workpiece, no, so that cavity or this that shape you have to give on your tool firstly. Okay, because if you give that inverse replica to the tool, then and then only it will produce on your workpiece. Now I will explain the working principle of this ultrasonic machining. Okay, so we have seen that electrical energy of high frequency is converted into the mechanical vibrations, okay, through the your transducer unit. Okay, so these mechanical vibrations are transmitted to the abrasive particles in the slurry, okay, via energy focusing device. Okay, and that energy focusing device means what? Your concentrator, or you can call horn, or that tool assembly. Okay, concentrator or tool holder or tool assembly or horn, everything is same. It is called energy focusing devices. So I once again repeat, mechanical vibrations are transmitted to the your abrasive particles which are present in the slurry, okay, via energy focusing device, and that is known as horn or tool assembly or concentrator. Further, that transducers are basically again, as we know that there are two types. One is the magnorestrictive type of transducer, which has certain characteristics, that is a low efficiency but it can produce high power. And another hand we have another type of transducer, it is called piezoelectric type transducer. Okay, both you can use. Okay, uh, the piezoelectric transducer has having high energy efficiency, but they do not require any cooling. Okay, so this is a no heat damage. Okay, there is no heat damage if you use the piezoelectric type transducer. Okay, but the problem is that its power capacity is very low. So, but in case of magnetostrictive type transducer, most of time you require cooling arrangement. It adds to the cost of your whole system. Okay, and but the some of the researcher have proposed that when abrasive particles are hitting the your workpiece, no, so that time erosion may takes place into one or more of three different modes, and that erosion means what? In one mode there will be the erosion, in second mode, okay, this is called colliding on the or sliding of your abrasive particle. In the third mode of that erosion, what will happen? Small scale that remolaction will be there by exciting the your that your abrasive particle. Okay, so that erosion will takes place. So this is a working principle. Understood? Now, I will give 2 minutes to draw this diagram. You can draw this block diagram as well as this one. So firstly, I will give time to draw this block diagram. So within 2 minutes, you have to write this. All of you, please draw this diagram. Don't leave meeting this. Okay, in between. Now draw this diagram. The same pattern. Actually, this is a schematic diagram of setup of ultrasonic machining. After this, we'll start with one by one elements. Function of every element we'll see. Okay, how you will get the waves. Okay, then how it is going to convert into the mechanical vibrations. Okay, having the frequency, ultrasonic frequency. Okay, then the role of the concentrator or purpose of concentrator. Then abrasives. Okay, now let us discuss the various elements of the your ultrasonic machining setup. Okay, just we have seen the setup. Now, which are the elements? So here I have listed that a sine wave generator. Okay, that wave generator, then a transducer, then tool holder, tool, and abrasive. Okay, so these are the elements. Now let us discuss one by one this. The first is a sine wave generator. Okay, so the sine wave generator normally converts your 60 hertz power supply, which we normally have in the our any lab. Okay, as well as our home. Okay, and to convert that 60 hertz power supply into frequency having more than or equal to 16 kilohertz. So the purpose of sine wave generator to convert 60 hertz power supply into frequency having more than or equal to 16 kilohertz. Okay, so this is the purpose of sine wave generator. Then we have the transducer. So this transducer uses piezoelectric crystal. Okay, which can have power up to 900 watts. Okay, as well as having the efficiency in particular case is very high. That is up to 95% efficiency is there. Okay, of this physiological crystal type transducer. I'm going to explain about the magnetostrictive type transducer also. Again, they are also used for ultrasonic cleaning and some other application purpose. Okay, these piezoelectric crystals. Okay, which are now normally they are used in non-destructive testing purpose. Okay, you can use even in very small, very low power ultrasonic machining uh, purpose also. So this is the first piezoelectric crystal transducer, and second we have the magnetostrictive type transducer. Okay, having it is having capacity up to 2.4 kilowatt. Okay, but here, as I have already mentioned, the efficiency is very low, 20% to 30% efficiency is there. But in case of this magnetostrictive type transducer, you always require cooling. Okay, and so it becomes essential. Okay, normally. But again, maximum amplitude of vibrations that you can obtain uh, in case of this magnetostrictive type, and that is up to 25 micron. Okay, so that much ma- maximum amplitude of vibration you can achieve because we require high frequency. Okay, ultrasound frequency, but your magnitude amplitude of vibration should be less. Okay, low. So for that purpose you can go magnetostrictive type transducer. Then we have the another element, that is tool holder. So there are two types of tool holders are there in case of this ultrasound. One is known as a non-amplifying tool holder, and another is it is called amplifying a tool holder. Okay. Again, in case of this amplifying tool holder, you can get a 10 times higher amplitude of vibration as compared to non-amplifying type of your tool holder. Okay. It transmit energy normally. Okay. This okay. Again, the amplitude of vibration can be as high as 1 micron to zero point 0.1 micron. Okay. Then another point is that tool holder material. Okay, and its property. So in that again, no commonly used some tool holder metals I have mentioned here. That is monel metal you can use, then titanium or stainless steel. So these are the metals we can use for your tool holder. Okay, because it have the good acoustic properties and resistance to fatigue cracking. Okay, again it should avoid welding, okay, between your tool holder and transducer during the working. Okay, now tool material. Okay, normally in that tool material you can use tool material like mild steel, stainless steel, brass. Okay, and the main property of the tool material are high ductility and high wear resistance. Okay, as far as surface conditions are concerned, it should have good surface finish. Okay, so there should be no scratches or machining marks on your tool. Otherwise what happen, they will be reflected on your machined workpiece surface. Okay, as well as some fatigue failure may occur uh, in your tool. Okay, because the tool is subjected to the very high frequency load changing. Okay, hence we can call fatigue failure of your tool may takes place. Okay, and if it has some scratches or machine mark, okay, then that will left on your workpiece also. Okay, again the tool design consideration for overcut, that should be uh, taken into the account, okay, at the time of tool design. Okay, so that you get the desired shape and size of your machine workpiece. Okay, you should minimize the fatigue problem by some silver brazing of your tool and your tool holder. Okay, you can minimize the fatigue failure. Okay, so this is about the tool. Then the important, that is abrasive. Okay, which type of abrasive we can use. So here you can see there are various kinds of abrasives used in case of ultrasonic machining, and some of them are alumina, that is Al2O3, then silicon carbide SiC, and boron carbide B4C. Okay, again the whatever the hardness of abrasives are there, no, so that should be definitely greater than the workpiece hardness. Otherwise what will happen, abrasive itself will fracture or break, rather than remove the material from your workpiece. Okay, again in that again selection criteria, how to select the abrasive. So while selecting the abrasives, following points should be taken care of. uh, okay, such as hardness, size of abrasive, life of the abrasive, and the cost of abrasives. Okay, then what is the workpiece material hardness? Okay, so in that again, that workpiece material hardness is again very important to know while selecting the abrasive. Okay, it should also be taken into the consideration, including the desired material removal rate and the surface finish. Okay, in that again, low concentration of abrasive is recommended for default drilling or complex cavity. Okay, again in that again, process performance, how to measure the performance. So material removal rate, surface finish, and accuracy. Okay, you can take grain size, mesh size. Okay, average of grain size 240 to 80, and the medium for the slurry you can take water or benzene or glycerol. So these are the mediums we can take for the slurry. Okay, because the out of the abrasives are there, no, so we have to carry. For that carry purpose we require carry medium, and normally carrying medium you can select as a water or benzone or glycerol. Okay, again in that, again low viscosity material or liquid like water is recommended because it can reach to the fine details or complex shapes easily. Okay, and again if it is having high viscosity, then what will happen, they may not be able to reach to the fine cavities or fine details on your component. Okay, so that water is recommended for as a carrier medium because having the low viscosity. Okay, but the problem with the water carrier medium is that it corrodes the workpiece. Okay, so one has to take this point also into the consideration. So this is about the elements, okay, or components we can call. Now next point is the fishbone diagram, that is called process parameter. Okay, now this process parameters and its effect we'll see in the next lecture. Okay, now wait. Now uh, now all of you, please write down the abrasives, which abrasives you can use for this. Please write down abrasives. Now, if you see in the average jet machining or average water jet machining or ultrasonic, okay, same abrasives normally wearing. So due to that point, I have covered that first point in the abrasive water jet machining. Okay, where we can use the different abrasives. So there I have explained this ultrasonic machining. Okay, now you can draw this diagram, a fishbone diagram of your ultrasound machining. Okay, through this diagram you will get the different process parameters which will affect the performance of your ultrasonic machining. And how to evaluate the performance. So for that purpose we have some characters, performance characters like material remove rate, tool wear rate, then cutting ratio, surface finish. Okay, and the formal geometry. So please draw this diagram. Okay, now I will show one animated video regarding working of ultrasonic machining. You can see. You can see how that tool holder or horn is vibrating. Okay. Now all of you, please write down your roll number in chat box so that I can write your attendance. गौरव तुळजापूरकर, ऋतिक ताटे, प्रेम तिट्टे, रोहन गांडोळे. रोल नंबर काय तुमचे?
Sir B60.
किती 60 हा ओके
सर 62.
ओके 62 लिहायला लिहायला
19
शुअर
सर 19.
ओके